Suppose we're looking at the scores for one component of the SAT. If 45,000 students took the exam with a mean of 528 and a standard deviation of 87, how can we determine what percentile a student who scored a 702 ranked? First, let's mark our distribution curve. Our mean is 528 and the standard deviation is 87. So plus 1 standard deviation gives us 615, plus 2 gives us 702, plus 3 gives us 789, but we don't even have to go that far. 702 is the number we're talking about. So what does percentile really mean? The percentile tells us better than how many percent a certain score is. So the percentile of 702 would be the number that tells us all the scores below the 702, what is the percentage of all those scores. And it tells us the rank that's better than how many percent of the overall students. So we're trying to find the percentage of the area which is below the curve from 702 all the way down to 0. To find that percentage, we again can add up the percentages of all the individual areas that are shaded, or more easily in this case, take 100% and subtract the areas that we don't need, and those are this area with 2.35% and the very top little area there with 0.15%. So 100 minus all those is 97.5%. So a score of 702 on the SAT of those specific 45,000 students is in the 97.5 percentile. What if a student scored a 680? Well, let's look where the 680 is. Uh-oh, we got a problem. 680 is somewhere here between 615 and 702, but it's not exactly at one of these borders. So how can we find the percentage of that if we have only part of this area? And as you can tell from the shape of this normal distribution curve, it's not proportional. So for that purpose, mathematicians have created a so-called zScore table where you can find all the percentages for all different z-scores underneath the normal distribution. Because remember, no matter what the actual values in the normal distributions are, the percentages underneath the curve are always the same. So in order to use that z-score table, we have to first find the z-score that's associated with the SAT score of 680. Remember how we find the z-score? We take the individual data value, subtract the mean, and then divide by the standard deviation. And for this particular score of 680, we get a z-score of 1.75. And that z-score is what we're going to use to find the probability in our z-score table. And here it is. And we will also practice with that z-score table in class. As you can see, it has a negative side and a positive side. And what it really gives us, and that's what this picture tells us here, it gives us the percentage associated with a z-score in terms of the percentage of the area to the left, and that's always the area to the left. For a z-score of 175, we have to go to the positive part of our z-score table. We got 1.7 here, and we move over to the 0.05, and that gives us a probability of 0.9599. 0.9599, which is the same as 95.99%. So that means that the score of 680 is in the 95.99, or you might as well say the 96th percentile. What percentage of students scored between a 480 and a 760. Again, looking at our normal distribution, we realize that neither the 760 nor the 480 is exactly at one of our borders. So we need to use our z-score table again. And what are we looking for this time? We're looking for a probability of a score of 760. So that would be around here. And that would also mean that the area represented under the curve is this whole area. But that is too much. And we then have to subtract all the ones that are below 480. 480 possibly being somewhere here. And all the numbers that are below 480 are the ones we don't want. So we need to find the z-scores and the probabilities associated with both of those areas, and then subtract our pink area from our green area. The z-score of 760 is 760 minus 528 divided by 87, and that is approximately 2.67. And the z-score of 480 is 480 minus 528 divided by 87, and that's approximately negative 0.55. Now we're going to use our z-score table and find the associated probabilities for both of these. For our 2.67, we are right here, 2.6. Go over to the 7 and we get 0.9961. 0.9961. And for negative 0.55, we go to the negative part of our z-score table. Negative 0.5 is right here. And go over to our 0.5, we get 0.2912. Now we need to subtract to get 0.7049 or 70.49%. Next, we're supposed to find how many students scored better than a 675. And again, 675 is also not one of our borders. It's probably around here. And this time, what we want is the area above 675. Our z-score table always gives us the areas below, though. What we have to do is we have to find the probability of the area below and then subtract that number from 1, because we know underneath our entire curve we got 1. First, we need to find our z-score. 675 minus 528 divided by 87 is approximately 1.69. What is the probability related to that? Let's look at our z-score of 1.69. In the positive part, 1.6 all the way over to the right, we get 0.9545, 0.9545, and that's the same, of course, as 95.45%. And we need to find out what's left from 100% after subtracting 95.45%, and that number is 4.55%. Now, we weren't asked for a percentage. We were asked for the actual number of students, how many students. Remembering that the total is 45,000 students, we need 45,000 times 0.0455, and after rounding, that is approximately 2,048 students. We can also do this backwards, of course. what score is in the 68th percentile and what score is in the 90th percentile. So here we are given the percentiles, which are equivalent to the percentages in our z-score table, and now we have to find the z-score from that, and then from the z-score the actual SAT score. So the 68th percentile represents 0.68 on our z-score table, so we need to look for the value which is closest to 0.68 and then read the z-score that corresponds with it. So as we're going through this table, here we see 0.6808, and that is the closest that we can find to 0.68, and the z-score related to that is 0.47. So 0.47 is equal to our data value that we don't know yet, minus the mean of 528 divided by the standard deviation of 87. So first of all, we're going to multiply both sides by 87, and we get 40.89 is equal to x minus 528. Add 528 on both sides, and we get x is equal to 568.89. And if we round this, because SAT scores only exist in full numbers, we get 569. The other SAT score is in the 90th percentile, so we need to look for the number that's closest to 0.9. We go down our table here, we got 0.9015, but right next to it we got 0.8997. And that, even though it's below, is actually closer to 0.9, and that's the value we need to take. And that is associated with a z-score of 1.28. So 1.28 is equal to x minus 528 divided by 87. And again, we're going to multiply both sides by 87. And we're going to get 111.36 is equal to x minus 528. Add 528 on both sides. We get 639.36 is equal to x. Round that to a full number. The SAT score is 639. Alright, now let's move on to two more real-world examples before we're done here. The useful life of a radial tire is normally distributed with a mean of 30,000 miles and a standard deviation of 5,000 miles, and the company makes 10,000 tires a month. What is the probability that if a radial tire is purchased at random, it will last between 20,000 and 35,000 miles? Remember, when we have a between problem, we need to figure out the probabilities for both areas and then subtract the lower one from the larger one. So first we want to find out what is the z-score related to the 35,000 miles, and that would be 35,000 minus our mean of 30,000 divided by the standard deviation of 5,000, and that is 5,000 divided by 5,000, and that's a z-score of 1. The other one would be 20,000 minus 30,000 divided by 5,000, and that is negative 10,000 divided by 5,000, which is equal to negative 2. This time we were lucky, we got integer numbers for our z-scores. That means we don't have to use the z-score table, we can just go from the percentages that we wrote into our normal distribution curve earlier in this lesson. If we go from negative 2 or 2 standard deviations below the mean to 1 standard deviation above the mean, we are including the three areas that have 13.5% and 34% and another 34% of probability. And as we add these all together, we get 81.5%. That's the probability that a random tire will last between 20,000 and 35,000 miles. And on to our last example of the day. The weights of eggs produced on a farm are normally distributed again with a mean of 1.4 ounces and a standard deviation of 0.4 ounces. To be graded extra large, an egg must weigh at least 2 ounces. What is the probability that an egg from this farm will be graded extra large? So let's first find the z-score of our value of 2. 2 minus the mean divided by the standard deviation. That's 0.6 divided by 0.4, and that is 1.5. So that's our z-score. For the z-score of 1.5, we are going to use our z-score table. Our 1.5, we got 1.5 and 0, and the probability of that is 0.9332. 0.9332. But remember, this value gives us the probability of all the values below 2. If we look at our normal distribution again, we want the values that are above 2 and not the ones below. So we need to take 1 or 100% and subtract the probability of the area which is below the 2 from that to get the probability of the area above. So 1 minus 0.9332 is equal to 0.0668, and that is the same as 6.68%. And there goes your answer. The probability that an egg from this farm will be graded extra large is around 7%. Alright, you guys, so much for this, and I will see you in class.